Now, suppose we obtain this support signal, we transmit through the channel, and channel everything is ideal. At the receiver, we receive the same signal. Now, the question is this. From this support signal, using this support signal, can we recover the original signal, original continuous time signal? The answer is yes, under the condition of the sapling rate specified by the Nyquist theorem. Nyquist theorem is also called sapling theorem. We consider a signal xt, which is band limited, which means that it has the bandwidth of W. The spectrum always equals 0 for the frequency outside minus W and W. That's the absolute value of f greater than W, which means f greater than W and f less than minus W. That's this condition, transfer two conditions here. If we sample the signal using the sapling period Ts less than 1/2W, and remember sapling rate is a reciprocal of the sapling period, which means that the sapling rate has to be greater than 2W, then it is possible to recover the original continuous signal by using all the samples here. It turns out that this is much easier to understand the sapling theorem in frequency domain. We will come back to this time expression after we look at the frequency domain. To look at frequency domain, we consider the support signal, which is a continuous time signal multiplied by the impulse train. Remember, our notation is that Fourier transform a continuous time signal, original signal, is a big XF. So the Fourier transform of the support signal, we call it x delta f equals to many copies of the original spectrum and scaled in the magnitude by fs. And mathematically, we have this infinite summations. Because this summation contains infinite terms, let's expand the summation using 5 different typical terms and to see what's going on inside the summation. We noted that all of the summations scaled by fs. Fs is the sapling rate. Fs equals to 1/Ts. Ts is the sapling period. So now if we look at n equals 0, n equals 0, then this term in the summation becomes fs multiplied by xf. And xf, that's the original spectrum. When n equals to 1, this spectrum is shifted to fs. The magnitude is scaled by fs. When n equals to minus 1, this original spectrum moved to minus fs. And I have all of this summation sign here because all of these terms contains inside this summation. And when n equals to 2, the original spectrum moved to 2fs. When n equals to minus 2, the original spectrum moved to minus 2fs. And we have many other terms. After the signal being sampled, then the spectrum become periodic. The period is EFS. You can see there is a replica of the spectrum from the original signal at EFS, 2fs, minus fs, and minus 2fs, and etc. Let's plot the spectrum of x delta f, which is the spectrum of the support signal. Let's assume that the original spectrum for the continuous time is this shape. The bandwidth W and minus W, the magnitude here is A. I'm using this triangular form, it's easier to draw. The first term is the same spectrum scaled by 1/Ts. The magnitude is scaled by 1/Ts. So this is, here is W, and this is minus W. When n equals to 1, this spectrum moves to fs. And here, this is EFS. I didn't mark it here, so this is Fs. Fs equals to 1 over Ts minus W. This point becomes 1 over Ts minus W here. That's this point. At the negative frequency, this spectrum move to minus Fs as minus 1 over Ts here. And there might be more here on both sides. Now, if we want to recover the original continuous time signal, what we need is a low-pass filter. So if we apply a low-pass filter here, the cutoff frequency can be anywhere from W to 1 over Ts minus W. So anywhere between here and here, I call it tilde, the cutoff frequency. As long as satisfy this condition, this low-pass filter can extract this spectrum out. This spectrum is the same as the original spectrum for the continuous time. And we know Fourier transform is 1-to-1. So if we have the same spectrum for frequency domain, so time signal, it has to be this signal. Therefore, from the support signal, we apply low pass filter, we can obtain the original continuous time signal. Now let's think about time domain. Frequency domain filtering using low pass filter, that is multiplication. Frequency domain multiplication corresponding to the convolution in time domain. And also we know this low pass filter here, this ideal low pass filter, time domain is a scaled sinc function. So therefore in time domain is really we have convolution of sinc functions. That's what we have here. Sinc function is time scaled by double to W tilde because the cutoff frequency is W tilde. Convolution contains summation of shifted sum of this sinc function. And this sinc function is scaled in magnitude by 2W tilde and the value of the support signal.